C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovib's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research, simplifying thermal conductivity.
Alrighty. Hello, everyone. Thank you so much for joining our webinar today. We really appreciate all the support. Just a couple housekeeping items before we get started here today. First, I'll introduce myself. My name's Emma Mattinson. I'm an analyst here at C-Therm Technologies, as well as a fourth-year chemical engineering student. Before we get started, I just want to let everyone know that today's session will be recorded. So if you have to drop off early, if you can't make the whole thing, it will be posted on our website later on for playback. Additionally, I will just ask you to save your questions, if you have any, to the end of the session, or make use of the chat box feature at the bottom of your screen. Alex and I will be having a Q&A session near the end of the event, so we'll try to leave some time to get to all your questions, so please post them whenever they come to you. So today's webinar will be on thermomechanical analysis, the theory and applications behind the analysis. So we're giving special attention today to thin film semiconductors and chips. This is what we see a lot of our clients bringing to the table when they come looking for some TMA testing or instrumentation. And the webinar today is presented by my colleague, Alex. He's our material testing engineer in training here at Thermal Analysis Labs. And we're very, very excited to have Alex walk us through the TMA analysis today. So just before we get started, I'll do a little bit of an introduction to who we are here at C-Therm Technologies. So we pride ourselves on being experts in thermal conductivity testing, and we are leaders in the transient methods. So not steady state methods, we focus on the transient methods. We have customers all over the world using the Trident thermal conductivity instrument in their research institutions and labs and universities. And we also have distributors, all over the world. So no matter where you're at, you'll always be in very good hands. So that's us, a little bit about us here at C-Therm. This device here, it's called the Trident. It's our main instrument that we've become experts in measuring thermal conductivity. So it's a very modular platform. A couple different sensors are available on it based on what your material is and what kind of samples you have. You might opt for one sensor or another. And while the webinar today is not on thermal conductivity or the Trident, I just wanted to make everyone aware of this product that we do offer. So this is a quote we like to use that really embodies the Trident instrument itself. So it's a famous quote: "When all you have is a hammer, everything looks like a nail." So this really embodies the Trident device. One of the issues we see a lot of times that results in poor data is when you have a really great method or really great instrument, but you're applying the method to the wrong sample type, a sample that the method was not designed for. So like I said before, the Trident is modular. And depending on your sample type, whether it be a liquid, a solid, a powder, a thin film, we can accommodate all of these different types of samples with one device. If you're new to thermal conductivity testing and interested in learning a little bit more about Trident and C-Therm and all the methods that we offer, this resource here is available as a free download on our website. The link was just put in the chat. So it's a very comprehensive report on all the different methods, which one you might want to select based on your sample type, and it is available to download on our website. So please download that if you're interested. And one other thing I want to bring up just before we get started here, C-Therm and our partners at Rigaku, we've developed a couple academic support programs. So these are for researchers in universities and institutions, academic institutions in North America. And just because we are really keen to collaborate with folks and help you advance your studies and your R&D efforts, we've put together a bit of a support program to offer discounts depending on the instruments that you're planning to purchase. The discount increases based on how many instruments you're purchasing, and we just really want to make sure folks have a really comprehensive portfolio and a toolbox of different devices for your labs in universities in North America. So these can significantly increase the testing capabilities of your labs. You can teach your students on these different instruments offered by Rigaku. There's a student bursary and all sorts of really great benefits on this academic support program. So if you think you may qualify, I advise you to please apply, and we would certainly love to work with your group. Finally, this is just a little bit about the different partners we work with. So you'll see in depth today a little bit more about our partners at Rigaku Thermal Analysis out of Japan. We offer their thermal line of products. So the DSC, STA, and TMA, which is going to have a special focus today. So we're very proud to work with them and distribute their product in North America, as well as Metrovib. So Metrovib is out of France, and we distribute their lines of DMA, so dynamic mechanical analysis. We have a brand new DMA on site in our lab, so if you're looking for some DMA testing, please feel free to reach out to us. We'll be happy to accommodate, and we're very proud to partner with them and distribute the DMA in North America. As well, you can see a photo of Alex there working with the TMA. We have a fully established thermal analysis lab on site here at C-Therm called Thermal Analysis Lab. So we do all sorts of different testing, DSC for heat capacity, and TMA, STA, DMA, all of the abbreviations that you might know of. We're very proud to have some very hardworking folks in the thermal analysis labs, and we can accommodate all of your different testing needs. So just before we get started, I will drop a quick client testimonial here. We're always so happy to hear what our customers have to say after they have worked with the Trident device and the C-Therm team a little bit. So this one is from Dr. Enrique Jackson from NASA. He says, we purchased a C-Therm thermal conductivity analyzer after seeing a demonstration of how fast and easy it is to operate. In terms of our satisfaction with the purchase, I'd give it a 10 out of 10, extremely satisfied. So we're very thankful for the feedback we get on the product lines, and very happy to be able to share the good feedback with you folks. So without further ado, I will introduce Alex here. Like I said previously, Alex is a material testing engineer in training here at Thermal Analysis Labs. Alex received his master's in chemical engineering a couple years ago from the University of New Brunswick, and he's actively pursuing his professional engineering certification, so his PEng. We're very proud to have Alex working with us here, and he's our in-house expert on the TMA and the different Rigaku products that we offer. So I'm very excited to have Alex on here today, and I will flip it over to him. And thank you again so much for joining us today.
Well, thank you for the introduction. Just going to share my screen and then we can get things rolling here. All right. So, as the priest mentioned, my name is Alec. I'm materials testing engineer in training here at C-Therm. I work in the lab with a bunch of various equipment, and my presentation is on the Thermomechanical Analysis, or TMA, its theories and applications. So, as mentioned, we do work with Rigaku. They are widely known for their XRD. However, they also do have a thermal analysis line, which includes TMA, Thermomechanical Analyzer, DSC, Differential Scanning Calorimetry, or the STA, which is Simultaneous Thermal Analyzer. So first off, before we dive into TMA, we'll just briefly go over them. What measures what? The STA measures heat flow, as well as the change in a sample's mass, the temperature. Sensor, a little bit more robust, has a wider temperature range. So it is great for, melting, crystallization, phase changes, decomposition. But also, some of the more finer things that require more sensitivity, it can do, but that is where the DSC shines. It also measures heat flow. However, it is way more precise, accurate. You can get all those small energy transformations, transitions. And then what this is on today is the TMA, which measures thermal expansion. And from that, you can get glass transition, total expansion, shrinkage, sintering, as well as the softening temperature. So CTE is an acronym that's going to be used a lot today in the presentation, so I'd like to go over it first to make sure we're on the same page. The CTE, or coefficient of thermal expansion, is a number that's used to describe how the material will change in size with a change in temperature. The units of CTE are micron per meter degree Celsius, parts per million per degree Celsius, or 10 to the negative 6 per degree Celsius. Now, essentially, all these things are equivalent, and when you mention when you're saying the same thing, personally, you'll hear me use the term ppm just because it's way easier to say. Now, when we quantify a change, we need a starting point. We need an initial state used as a guide, so all CTE values will or should have a reference temperature. This means that starting from this point, this is how much it expands from. So as we can see here on our graph, corner out, our formula for CTE is here, where we have our little 0 as our initial starting point, and then our variable without a subscript is the point we're interested in. So here we see we have a reference point. This is what we're saying our expansion is in reference to, and this is the point that we're talking about. So why is CTE so important? Firstly, it's always useful to know how a material will behave at different temperatures. Some applications require materials to be, constant and steady over a wide range of temperature, while others, they want to see a shrinkage, they want to see a expansion. Also allows us to determine density as a function of temperature. Density is a pretty important parameter. It's used in a lot of, equations, models, and it's just good to know. And getting the expansion and contraction, we can note over a wide range of temperatures. Also, in some undesirable scenarios, thermal expansion can lead to either internal stress and then cracking or even failure. So that's always good to know, is how much your material will expand. And as well for material pairing, if the materials have a large CTE and there's a temperature change, it can cause warping, delamination, or even failure. This is important when working with composites, stack, substrate deposition, especially relevant in electronics and semiconductors. So additional things for CTE is when rapidly or unevenly heated, some materials do experience thermal shock due to the sudden or uneven expansion within it. Brittle materials like ceramics and glass are especially vulnerable to breaking, shattering. So it's often best to avoid thermally shocked materials that have a low CTE. Cookware is a good example. You put boiling water in room temperature mugs or cups or bowls, or even baking dishes are quickly moved in and out of the oven. Ceramics with a lower CTE will expand less, and therefore you'll experience less stress. So for this reason, some glasses and ceramics are formulated specifically to have a low CTE for applications like these. That's just one reason why knowing the CTE and fine tuning it is important. Continuous structures like railroads, bridges, pipelines. Remember how the total expansion is based off a reference or an initial length? This makes really long continuous structures susceptible to shrinking, which can cause fractures or cracks, and expansion in the heat, which can cause warping or buckling. For this reason, joints or spacers are often used to prevent buckling. An example here can be seen on the bridge, where there's a spacer which allows this one section to freely expand and contract, removing stress from the bridge. And on the left here, we can see a railroad, where around just right here, we can see it is warped. So we definitely don't want that. Another application, medical application. You have to consider that when an implant or medical device will enter the body, it's going to heat up to match the body's temperature. So if you've designed it around room temperature, how do you know it's going to act at a body temperature whenever it expands or contracts? Wearables, braces, prosthetics, you don't want them to shrink or grow, loosen or contract, apply too much pressure. An interesting one is dental fillings. If the filling expands too much, it can apply some pressure on the tooth, cause some pain. An expansion might occur due to drinking hot coffee, or even contraction might be from eating something cold like ice cream. Additional applications, you have precision machining. When you're machining a metal or a part, friction used to cut it or trim it causes it to heat up. But when it cools back down, is it going to be the same length that you want it to be? Or if you're connecting two dissimilar metals and they go through a temperature change. Are they going to warp? Are they going to get stuck? You kind of need to know what's going to happen. How will they react? Additionally, systems that are exposed to high temperatures, furnace, engines, exhaust system, reactors, other aerospace applications as well. One interesting thing to think about is satellites. As they orbit the Earth, they're constantly moving in and out of the Earth's shadow. So their temperature is cycling from cryogenic to scorching hot multiple times a day. So something that maybe we don't understand or why it happens, or something we even do in our own life is if you have a jar that's stuck, run the top under hot water. Some of you might already know this, but it helps loosen it and it lets the lid be removed because the CTE of metal is much greater than the CTE of glass. So your metal lid is going to expand much more than the glass rim. That way, you can easily loosen it up and take it off. Lastly, before we get into some more technical things, I have a couple of fun facts. Eiffel Tower is 330 meters tall, and it can grow by 10 to 12 centimeters in the summer. And then Invar is an alloy that contains 64% iron, 36% nickel, and has the lowest thermal expansion of any metal. So as we can see, whenever we combine some alloys, it's not just a ratio of one and the other to get thermal expansion. Up here, we have our iron, pure iron CTE. Down here, we have our pure nickel CTE. Then as we combine them and the percentage of nickel grows, we can see we get a sharp curve where we have Invar right here. We have very low thermal expansion. That just goes to show that you can't really predict CTE sometimes, and it's based off things like, crystal structure and such. So some materials, such as water and gallium, exhibit a negative thermal expansion. So as you heat them up, they can shrink. Also, as you cool them down, they can expand. So now we're going over a little bit of the Rigaku TMA instrument itself. So it is a vertical push rod dilatometer, which means that you have a vertical rod that sits on top of the sample. And then as the sample expands, it pushes the rod upwards, and that's what is measured. Temperature can go as low as negative 150 degrees Celsius, as high as 1500 degrees Celsius. This is achieved by 3 different furnaces. So you have your cryo furnace, which can go from negative 150 up to around 600. Your standard furnace, which goes from room temperature up to 1100. And your high temperature furnace, which goes from room temperature all the way up to 1500. Temperature and accuracy is plus or minus 1 degree Celsius. Ideal sample size, 10 to 20 millimeters tall. And the, the measurement range, like the total expansion or shrinkage, 2.5 millimeters. And then the detector, 20 nanometers. So it gets pretty precise, and the digital resolution, the number it will give you to the nearest 0.3 nanometers. And the force that the rod will exert on the sample whenever it's resting, you can change from 1 to 1,000 millinewton. So we'll go over some attachments because the instrument can do multiple things. It's not just a one-trick pony. So the first one we have is compression differential. Here we see the differentials reference to, we have 2 rods. We have 2 detection rods, and we have our sample, and then a reference sample. This is the most accurate way to do TMA, and it's really good for the low expansion and precise measurements. Next, we have our single rod or non-differential. Same thing, except there's only 1 rod. And we have our tension thin films. So things that are, not the bulk, as I'll call them. This one does use tension instead of compression. And then there's some other niche ones like penetration and 3-point bending. These I'm not really going to be speaking about today. So for compression, what type of samples do we need? What sample size? So it's good for polymers, ceramics, metals, and rigid insulation. Shape, it should be a rod. Height between 10 to 20 millimeters. Recommended diameter 3 to 9 millimeters. But it's really important that for the samples, the top and bottoms are flat and flush. So here we have our ideal sample where the top is flat, it's flush with the rod, it's flush with the support tube. It's great. Here we have an unideal sample where we can see it's kind of warped to the right. The top and the bottom aren't flush. So the rod is not going to sit as well. When we record the expansion, we're not recording it straight up the vertical axis. It's a little bit sideways. So the way that the vertical push rod dilatometer works is that we have our sample We have our detection rod that sits on it. The downward force is applied, keep it in contact and snug. And then as this expands, it pushes the rod upward, and that's what measures the change. The reason for the recommended diameter from 3 to 9 is because as the sample gets wider, it creates the possibility for a non-uniform temperature distribution. So what that means is that you can run into a possibility if the sample is too thick, where the temperature on the outside of the sample is way hotter than the temperature on the inside. So it decreases the accuracy. And if your material is going through a transition like a glass transition, it's possible that the inside is still very sturdy and in the glass state, but the outside is in the rubbery state. So it can kind of give non-ideal results in that way. And then if the sample is too thin, it makes it hard to be freestanding. It can be toppled over. It's hard to set. So that's kind of why they give this ideal range. So for a compressive loading, here is the regular, the single rod non-differential. As you can see here, it is made of quartz, so it makes it hard to see what's going on because everything's transparent, which is why I have this picture over here. So what we see is first off, we have a thermocouple. In this picture, it's kind of situated behind the rod. It's hard to see. That measures the temperature inside the support tube. Here we have our sample that's on the support tube, and then our detection rod, which again, as the sample expands, it pushes upward, and this is recorded by the electronics. Here's the compressive loading. As we can see here, we have our reference sample, goes in the left side, and this measures the expansion of the reference sample. We have our regular sample, which goes on the right side. We have this detection rod, and then the support tube, same as before, but this time our thermocouple is a little bit longer, and it goes around. This allows us to place it inside the reference sample. This is done because the closer it is to the sample, the better temperature results you're going to get. Because if you're measuring the temperature of the sample and your thermocouple is all the way over here, you're measuring pretty far away from the sample. What we do here is we curl it upside down, we put it inside the reference, it gives a much better temperature reading. What you can also do is you can also have it touch the sample if you know that it's not going to melt or fuse to it. So the difference between the single rod, the non-differential, and the regular rod. So when heated, the sample holder, the detection rod, and the support tube will also increase. So the observed expansion or measured expansion is actually what the sample and the detection rod support tube. The thing can't differentiate between the two. This is why we use quartz. Quartz has a really low thermal expansion, roughly around 0.5 ppm. This is why all the components are made of quartz. For this reason, the singular rod works best on materials like polymers that have a very large thermal expansion. The theory here is that the expansion of a polymer is 10,000 times more than the quartz. So at this point, it's really negligible. Another benefit of having one rod is that there's much more free space in the support tube, meaning in theory, you could have a little bit wider sample, but then again, you have to watch out for the temperature distribution. So differential TMA is highly effective for materials with low thermal expansion and when you need to be more precise. Examples include metals, ceramics, alloys, and a bunch of other different stuff. So in the differential mode, the observed expansion, or what is measured, is actually the difference between the coil, which is the reference side, and the core, which is the sample side. So the coil here sees the expansion of the reference side, and as well as the detection rod and support pipe. The coil side sees the expansion of the detection rod, sample, and support pipe. Then the observed is actually the difference between the two. So because it's measured on each end, it cancels each other out. So as we can see here, the coil and the core both have the detection rod support tube. The observed is the sample minus the reference because these two cancel out. We know the observed, this is measured. We know the reference because the reference we use is a standard with known values. So just by doing simple rearrange, we can easily determine to a high degree of precision the expansion of the sample. And that's kind of the beauty of it. So what are the advantages of a differential method? In my opinion, the differential TMA is necessary for very low temperatures and very high temperatures. So the CTE tends to increase with temperature. So at very, very low temperatures, there's not very much expansion. And when there's very little expansion, you really need to be accurate and precise to avoid large errors. So this is why it's important below -40. And then quartz softens around 1100. So we can't really use it anymore, meaning that now we have to use alumina for our sample holder. As we can see here, we have the differential with alumina, sorry, the side alumina, and this side is quartz. So quartz or alumina has a CTE of around 5 ppm, or roughly 10 times more than quartz. This means that the error we get will be around 10 times more. And also, only materials that go above 1100 are metals and ceramics, which generally tend to have lower CTEs. This is why you absolutely need the differential method to cancel out the expansion of the holder and the pipe, support pipe, and the detection rod. Additionally, I did mention earlier that 10 millimeters is the lowest we can go. That's not entirely true with differential. Because it's so precise and accurate, we can measure samples that are way less than 10 millimeters thick. We can actually measure the expansion of samples that are close to less than 1 millimeter. So we really need differential here for the precision, because the smaller the initial height or length means a smaller overall total expansion. So we're measuring a really small amount of expansion. This is especially useful for measuring the expansion of wafers, substrates, circuit boards, and the other electronic parts that you can't really manufacture them thicker. And if it's harder, or if you do, it might not be as accurate or representative of what you want to use it for. Another niche application I've noticed for really small sample sizes is some groups synthesize their own materials. And when they make their own materials, sometimes it's expensive or hard, and they can't really get enough to form a 10 millimeter tall rod. So for them, it's a lot more feasible to create a tiny pellet with a height of like 1 millimeter and then do the expansion of that. Before we move on, there are two types of detection rods that you can use. You have the one on the left, which is the arc type or point contact. This one just has a rounded base, so it actually focuses all the force into a small area for a high amount of pressure. This is, creates good contact, but it's only ideal for metals and ceramics, other alloys, where there's no chance of your sample softening or deforming. On the right, we have the flat type, which helps spread out the force, distribute the force, less pressure. This is ideal where there's samples could be deforming, such as polymers when they get soft. So that's just kind of some things that are thought about whenever the TMA is designed. And so moving on to our tensile loading sample size, this is good for non-freestanding things, such as polymer films, metallic foils, fibers, fabrics, wires, Thickness we can do around 10 to 30 microns. Sample size, width, about 5 millimeters, and the length, there's an option for 10, 15, or 20 millimeters. So a jig is used to actually cut it to these dimensions. And then as well, a different jig is used to secure the clamp to the sample. Because we can see here, the sample is on clamp. It's in there as well. So when the theory here is that instead of applying, a compressive force, we're pulling the sample. Because thin films are flimsy, if you were to try and compress one, it would just bend and buckle, and it's just really doesn't work very well. So here's a little bit about our thin film mounting jig. So we have, these are the brackets. The spacer goes in, and then you insert your bracket. Then you place the sample, place your upper bracket, and close it. I was mentioning earlier how CT is important for, precisely machined things, and that's kind of what this is. This is precisely machined so that everything fits snug, and every time it's either 10, 15, or 20 millimeters in length. So moving on to some data analysis, kind of what you expect to see from TMA, what you can interpret from the results. So we're starting off with something nice and easy. This is just linear expansion. I believe this is a nickel. On our left here, we have a plot that has total elongation in microns. Down here we have time, and then on the right we have temperature. So as you can see here, there's a little bit of a startup zone where it's kind of round, and then once it kind of catches up, it's fairly linear. So here they chose to do a base temperature or a reference of 50 degrees Celsius. And then here you can see the length in a number, the expansion percent, and then the CTE. So personally, whenever I do something like this, I like to start the test a little bit beneath the reference temperature, and you can see exactly what that was done here. The reference is 50 degrees Celsius because there's a little bit of startup curve, so you want to have your reference temperature kind of past that point. Moving on to a glass transition. On a TMA, a glass transition, where a substance goes from a hard glassy state to a malleable rubbery state, can be shown by a change of rate of expansion. So you see here we have a linear zone that is the glass zone. We have a little dip, and then all of a sudden we have another straight zone. This is the rubbery zone, and then we define it as the intersection of these 2 points. So we're to follow this line straight, it leads here. Follow this line straight, leads there. And then you notice up here at the top how there's 2 reference temperatures, or T naught. That's because here what has been done is they noted that there's 2 linear zones. So if you have one reference temperature here, we can have a linear CTE zone. But then whenever we change, we do our reference temperature here. That way we can do it solely in the second zone. It just makes the second CTE a little bit more stable, because if you use here as a temperature reference for the entire thing, it will steadily increase instead of keeping it in a linear zone. Here we have a glass softening. We can observe again the first linear zone from the glass region, and we can observe the rubbery zone. And then up here we have what appears to be shrinkage. This is actually the dialectometric softening point, and it's less of a material property, but more of an artifact of the methodology. As you may recall, the sample sits on the support tube and the detection rod is on top. It pushes down on it, applies a small force, 1 to 1,000 millinewtons. Eventually, the sample will reach a point where it can no longer support the force applied by the detection rod, and the rod will actually begin to, penetrate the sample. So in reality, the sample isn't shrinking. This is just what the machine sees. So because it's less of a material property, more from the method, it's really good for comparison. If you have different glasses, polymers, whatever you'd like, and you kind of want to see what temperature they get soft at, you could run a test, or tests rather, with the same condition, but repeat it with different samples. Next, sintering, very popular with TMA. In ceramics, prior to doing the final product, you have to fire the ceramic, put it in a kiln, oven, whatnot. And before doing that, you have to shape it. So what is done is they take, ceramic particles, powder, you mix it with a binder, and then that kind of helps keep the particles together, give it shape, and then you press it down into the shape you want, in a press or a punch or whatnot. And the binders tend to be organic, so as you heat them up, they burn off. And then now we're left with the ceramic particles have kind of voids in between them, spaces of air. Then as temperature increases, they don't melt, but they tend to soften and want to stick together. So this sintering is the densification of ceramic. And as we can see here in TMA, we can actually find the point where this sintering begins, because it's densifying, it shrinks. So we say, okay, the shrinking starts at X temperature, and then we can do the final percentage. So we can see here, this one was just shy of 20% is how much it shrunk. So you can kind of use these to create your formulations or percentages of binder to ceramic ratio. You can try sintering and shrinking with different ceramic particle sizes. There's really a lot to go on here. So here's a test that was done to see how copper thin films, this was done using the thin films attachment, how copper thin films handle elevated temperatures over extended periods. Here's the setup. 30 micron thick copper thin film was strung at 100 millinewtons, and it was held for 1 hour at 6 different temperatures, or five, sorry, at 5 different temperatures. And I'll refer to them as isotherms. So we have isotherm where the temperature isn't changing. We can see here that during the first two, during this temperature hold, the expansion stopped. Makes sense. Temperature's the same, no thermal expansion. Here, the temperature stopped, so did the expansion. But once we get to around 300, we see that although the temperature didn't change, we did see a little bit of expansion. And then up at 400, during the hour-long isotherm, we see that there's a little bit more. And then all the way up at 500, we see that even though the temperature wasn't changing, the sample was still deforming. So really, that just goes to show that, you know, sorry, kind of messed this up. So I'll start over. After the run, we can see that the length didn't return to its normal length. So there was some permanent deformation applied. Something irreversible happened, and we can never get the copper thin film back to the initial way we started it. So this test was designed to kind of emulate how copper will behave whenever electronic overheats. So, the takeaway is that if it overheats to, 100, 200, you can still kind of salvage it. But once it hits 300, 400, 500, you get irreversible damage happening to the copper thin film. So here is the before and after pic. I was initially planning on labeling them. However, I think it's clear that copper film isn't supposed to look like this. So this is the same data, it's just presented differently. Now we have a thermal hysteresis curve. So we can see here that instead of time, we have temperature down here on the bottom. So we have our first isotherm. Not really noticeable. Makes sense. We didn't see much expansion. Second isotherm, again, it's very negligible, comfortable holding at 200 degrees Celsius. And once we reach above 300, we can see that third isotherm did have some notable expansion. And then our fourth isotherm, we see that, yes, the sample is getting damaged, something's happening. And at the fifth one, it's very easy to see that something irreversible is happening to the sample and it's never going back to normal. Then from this, we can also measure that there was around 140 microns of permanent deformation done to the sample. So our next application is on a printed circuit board, or PCB, by differential compression method. So PCBs are normally composed of epoxy resin reinforced with fiberglass and electrical components on top, and as well as copper layers inside. Something to note here is that the sample length is less than 2 millimeters, meaning that this was done with differential, and that this, at this thickness or height, only differential can be used to measure this. So in this application, a 10-year-old PCB board versus a brand new PCB board were both tested, and the results were compared. So as we can see here, up until around 120-ish, the expansion is quite the same, but then the old PCB goes through the glass transition a little bit earlier, and then the expansion is just much more than the new one. And then quantifiably, we can look at the CTE values, and we see that around 40, pretty similar, 100, pretty similar, 120, we're starting to get a little bit of a difference, and then after that, the old PCB is a lot, it expands a lot more. So that's, don't really want PCB boards expanding overly. They're bolted down, they're in small compartments. This could be as a result of, aging, components being worn, contamination, etc. So here's the TMA of multi-layer ceramic capacitors in a dry versus a wet environment. So multi-layer ceramic capacitors are electronic components, and they're made by alternating thin layers of metal and ceramic simultaneously. Barium titanate is one such example, and the study, or the testing was performed on the sintering of a plate that contained 14 weight percent ethyl cellulose. This is the binder. Again, ethyl cellulose, organic because it needs to burn off, and as well as barium titanate. Again, take note that the sample thickness is 1 millimeter, meaning that this can't be done using regular TMA. You do need differential. So the main point of this test was to compare the effects of the atmosphere on sintering. The atmosphere under which ceramics are sintered or fired can significantly influence their properties. This test was used as a dry versus wet atmosphere. However, some electronics are also fired in inert gas, reductive gas, or oxidative gases. We can see here our conditions are room temperature to 1300. We have one test where a dry atmosphere was being pumped into the TMA. We have another one where a wet atmosphere, so 60 degrees Celsius and 80 RH, that was the gas being pumped into the furnace. So as we can see here, the blue is the one that was wet and the green was dry. The blue did begin to sinter sooner, and it sintered at a much greater rate. And at the end, it had shrunk more. That's kind of the brief takeaway you can see just by reading this. But what else can this tell us? If the mass of barium titanate doesn't change, but the material will shrink more in a wet environment, this means that in a wet environment where there's more, the same mass but more compact, that the material will be denser, it'll be stronger, it'll be harder, as well as more thermally conductive. That's one of the reasons why they chose to do dry versus wet, is because in some applications, this is done in a wet environment for these exact reasons. And when we kind of do science, sometimes we like to do it in a vacuum where we do no moisture, no humidity, no loss, we have a steady heating rate, but sometimes that's not really a good representation of the real world. So with the humidity attachment to the TMA, it allows you to, add one more variable to your studies. Next, here are some results from a scientific paper that was published, and they used a Rigaku TMA for a thermoelectric generator research. As the name would suggest, this is an apparatus that harnesses electricity from a temperature gradient. So these work by employing a stacking thing similar to the MLCC. So they have your P-type semiconductor, your N-type semiconductor layer, as well as an insulator. They take a bunch of different layers and they stack them all together. So the P-type was a 20 weight percent lanthanum strontium titanate. The N-type was a nickel molybdenum, and the insulator was yttrium doped zirconia. So typically the components are stacked together and then fired together at 1300 degrees Celsius for 2 hours. But in this study, what they've done was they fired them individually just to see how they would, react and see if they're a good fit for each other. So here we see the TMA result from the individual components. They do inhibit similar properties. So, they sinter around the same temperature, they have the same shrinkage, which means that they're, compatible with each other. However, from this, we can clearly also identify that the insulator starts shrinking a little bit later, and that the N-type has the least amount of expansion, but it's not by much. This looks to be 13, and then the other one appears to be 14. So just, small, precise things like that you can see. So thank you. I'd like to thank everyone for coming to my presentation, as well as Emma for, introducing me and organizing this. I think we do have some time for questions, but I think there might be a little outro done prior.
Awesome, Alex. Thank you so much. I will do just a very quick outro here, just so we can save enough time to go through your questions that are in the chat box. So as my PowerPoint's coming up here, if you're interested in watching any of our past webinars, they're all available on the C-Therm website. So all of the webinars that we've had in the past are available for playback. And you can see the upcoming webinars there as well. If you're interested in reading any of the publications that use C-Therm, Rigaku, MetroVib data, those are also all available in the tech library on our website. You can search by keyword and find exactly what you're looking for on the website. If you're interested in C-Therm or MetroVib or Rigaku, we are totally open to doing live demos and technical consultations. I have many team members here that are experts in the fields of different thermal analysis and material characterization techniques. So if you're interested in seeing a live demo, we'd be more than happy to coordinate that. And of course, if you're liking what you see and you're ready to potentially make a purchase, I advise you to please request a quote. The team's always quick to act on those, and you can get feedback within a matter of hours or a day or two. So there's a request a quote link in the chat box there. Please make use of it if you feel inclined to. Again, I just want to highlight the academic support program. So if you're doing some research and you think some of the Rigaku instruments might be helpful in your research, please, if you think if you qualify, please fill out the link on our website. That was also put in the chat just now. There's many different benefits to this program, but really we just want to help you with your research and to accelerate some of your testing in your facility. Finally, you can follow us on LinkedIn. You'll see all of our upcoming webinars on there, different publications, different events that we're going to be at, and all sorts of different updates. So that's probably the fastest way to see what's going on here at C-Therm. So please give us a follow. And for the upcoming webinar, so our next one will not be next week, but the week afterwards, so December 5th at the same time as today. We have a special guest, Dr. Chris Robertson. He's a consultant at Polymer Technology Services, and he's really, really an expert on MetroVib DMA, so works with many different folks using the DMA and is very, very knowledgeable in that field. So he's going to be chatting about using DMA to characterize the glass to rubber softening transition of polymers. And I'm sure it will be a really, really great talk. So please register if that's something you might be interested in. And finally, to cap off 2024, we'll have another special guest, Dr. Anurag Roy from the University of Exeter. He is a research fellow, and he's recently published some work using the C-Therm device, the MTPS in particular. And so his presentation is called The Role of Thermoelectric Materials in Sustainable Building Design. So some really interesting research going on there, and we're very excited to have him come present with us. Where we will be in the coming months. So we just have one show planned for December, the Adhesives and Bonding Expo in Europe. So my colleague Ed Park will be at our booth in Germany, booth 1006. If you're in the area, Ed would be more than happy to chat with you. So we will be there the first week of December. And now I will invite Alex back on here, and we'll go through the Q&A. So I see a couple of questions in the chat box here. The first one, we were actually chatting about this yesterday. So Alex, what is the difference between TMA and dilatometry?
I guess you could say one is the other, but the other isn't one. TMA is the study of how the material will not react, but how it acts as you heat it up in terms of thermal expansion. And then dilatometry is just a type of TMA, one that uses a negligible force. So as I mentioned before, the rod sits on top. We set the force to around 10 to 1,000 millinewtons. That's considered negligible. There's some other TMAs that also they measure expansion using fluids, or some use lasers as well. So it's just a dilatometer is a type of TMA.
Awesome, thank you. The next one, how can we make samples for TMA? Do you do it by molding?
I guess it really depends on the type of sample you have. If we're assuming we're using something like bulk or compression, then if it's a polymer, then you can easily cut it out and then shape it like that. If it's a ceramic, you can mold it. If it's sintered versus unsintered, you can press it into a pellet and then either fire it into the shape. So you can mold it. Some metals do machining or even 3D printing. Essentially, any way you can get it into the correct shape is fine. I guess there's no wrong way to prepare a sample, because it's based on your application. If it's representative of how you'll be using it, then that's fine.
Perfect. And Alex, can you explain a little more about how the thin film sample is mounted on the TMA?
Yeah, of course. And if I could share my screen again, I do have a video we can look at.
Sure.
Pretty long, so I might fast forward some of the parts. Here we go. So here is a close-up of the thin film jig that is used to set or clamp the sample. So we start off by setting or putting the spacer in there, and then we put the bottom clamp. And then from here, we have our we put our sample in, and then we set our spacers. And the point of the spacers is to make sure that the sample is, or that, sorry, the clamps are set and that they're in the good position. You want it to be very precisely 10, 15, or 20 millimeters. So you actually push them in as much as you can while you screw it. So you see here, pushing while this is screwing to make sure that it fits snug. You do it on both ends. Then moving forward, we place our top clamp on both sides, and then we start our second mounting, where we do the same thing. We actually push this metal bar into the clamp to make sure that it's snug and set in the correct position. You can see here, pushing and then securing. And this is kind of what the finished product will look like. And then to get it out, we just do reverse order operations. We loosen all of our clamp. And then we just remove it. Yeah, maybe we can post this video somewhere just so that people can watch the full 5 minutes instead of me skipping every 30 seconds.
Yeah, sure. Good idea. Very cool. Thanks for sharing. Just one last question here, Alex. Can the TMA actually detect the binder burn off that you were talking about?
You see, TMA measures, change of length. So if there is change in length associated with the binder burn off, it can see it. However, I think there's better methods to do that. If you remember, I mentioned Rigaku also has an SPA, which can measure mass loss over change of temperature. That's probably the preferred method for looking at binder burn off because you can actually see the point where it starts very clearly, as well as the total amount you lose. So if you have a mixture that's 14% binder, you can burn it in the SPA and you'll see a 14% mass loss. As well, you can also try with different gases. Oxygen is obviously going to burn. If it's in inert atmosphere, it's going to thermally decompose. And depending on the environment, it's going to, burn off or decompose at different temperatures.
Awesome. I think that's another great example of why it's important to have maybe more than one device in your tool set. They each have their own advantages in different applications. So very insightful, Alex. Thank you.
Yeah, it really is synergy between the instruments.
Yeah, absolutely. Absolutely. I don't see any more questions. So if there are no more questions, I guess we can end it here. But thank you very much, Alex, for the presentation. It's fantastic. And thank you to all of our viewers today for joining us. Hope to see you on the next one. If you have any questions, please direct them our way, and we'll be happy to help. So have a great day, everyone, and thanks again for joining.